We're now going to focus on some more techniques for finding closed formulas for recursively defined sequences. So the two techniques we're going to look at are called telescoping sequences, and the other is called iteration of sequences. So let's look at an example. Suppose that a0 is equal to 3, so this is the first term. And then our recursive formula is going to be an equals an minus 1 plus 4 whenever n is greater than or equal to 1. Now, as we've seen, this does generate a unique sequence, and we've also seen this particular sequence before. It's an arithmetic sequence, which is nice because we know what the formula is, so it's a very nice sequence to try out a new technique on, right? So when we get to the end formula, we can see that, oh yeah, that's consistent with what we've been doing before. So instead of kind of finding patterns like we did before, we're going to bring the an minus 1 over to the left side of the equation by subtracting it from both sides. We get an minus 1 equals 4. And then we're going to list some of these equations for different values of n. So if you have n equals 1, you have a1 minus a0 equals 4. If you have n equals 2, you have a2 minus a1 equals 4. If you have n equals 3, you have a3 minus 2 equals 4. You keep on going. Your second to the last one is going to be n minus 1. That is an minus 1 minus an minus 2 equals 4. And then here's what it looks like for n. An minus 1 equals 4. So one of the things you may notice is that when we add up on the quantities to the left, there's going to be a lot of cancellation happening. So for instance, if you look at that first equation on top, you have a minus or a plus a1, but in the second equation, you have a minus a1. So when you add those two, the a1s are going to cancel. Similarly, in the second row, you have a plus a2, and in the third row, you have a minus a2. So when you add those, the a2s are going to cancel. And you can't see it, but that a3 is going to cancel with whatever is in the n minus 4 row. And almost everything is going to cancel, except there are going to be two who escape. The minus a0 at the beginning never gets canceled by anybody, and the an at the very end doesn't get canceled either. But everything else gets canceled, so we end up with an minus a0. If we add up all the quantities on the right, well, we just get a bunch of 4s. The question is, how many 4s? Well, we get 1 4 for each row. We start at n equals 1, we end up n equals n, right? And that ends up with 4 copies of 4, so that gives us 4 times n. Now, when we add up the quantities on the left and the quantities on the right, those are literally the same quantities, right? Because each of the quantities that we're adding are equal to each other. So that tells us that an minus a0, adding up the quantities on the left, equals 4 times n, adding up the quantities on the right. And now it's just a matter of solving for an. We want a formula for an. We get an equals a0 plus 4n. And you may not remember, but our initial term, which we had to define because it was a recursively defined sequence, was a0 equals 3. So we put that in to get an equals 3 plus 4n. And if you look back at the recursive definition, this is exactly the formula that we got for arithmetic sequences. So it checks out. All right, so this technique is called telescoping. For our next technique, we're going to have a slightly different sequence. We have a0 equals 5, and we have an equals 3an minus 1 plus 1 for n greater than or equal to 1. And you notice that we have that 3 in front of the an minus 1. And as you'll see later, this indicates that trying telescoping on this one is not gonna help. The cancellation isn't going to work like we want it to. But fortunately, we have another technique that we can use. And what we're gonna do is look at some examples and see if we can see some patterns. Now, remember that when we look at patterns, we want to be a little bit stupid, which means we don't want to simplify too much, because if we simplify, we can lose some of the patterns that we end up with. We just want to simplify enough to help us figure out what the patterns are. So a0 equals 5, that's our first one, not terribly exciting. For a1, we put in n equals 1 into our recursive formula. We get a1 equals 3a0 plus 1. We know a0 is equal to 5, so we plug that in. So we get 3 times 5 plus 1. You may be tempted to call that 16, which is absolutely true, but it turns out that's not going to be helpful. So we're just going to leave it as 3 times 5 plus 1 for now. Now when we plug in n equals 2 into our recursive equation, we get a2 equals 3 times a1 plus 1. we have a nice formula for A1, 3 times 5 plus 1. We can plug that in. Now we've got to be a little bit careful about how we simplify. We can see that if we just leave it like that and keep using recursion to figure out A3 and A4 and A5, the parentheses are going to get maddening. So we do want to get rid of the parentheses, but we don't want to simplify things once we multiply through the parentheses. So when we multiply that 3 through, we're first going to multiply 3 by 3 times 5, and that's going to give us 3 times 3 times 5, or 3 squared times 5. And then we're going to get 3 times 1, that gives us plus 3, and we want to leave that as is. Now, oh yeah, we also have the plus 1 at the end, okay? So that's what we get for A2, and it looks a little bit messy, but much better than having the parentheses. Now, if we plug in n equals 3 into the recursive equation, we get 3 times A2 plus 1. Fortunately, we just got a nice expression for A2. And we're going to try the same trick of multiplying the 3 through, simplifying by using the distributive property, but not by anything else. And multiplying by the first term gives us 3 times 3 squared times 5, and that's 3 cubed times 5. Then we get 3 times 3, which is 3 squared. Then we get 3 times 1, which is 3. And then we get another plus 1 on the end. If we play the same game with A4, we plug in our expression for A3. We multiply the 3 through very carefully. We get 3 to the 4th times 5, plus 3 cubed, plus 3 squared, plus 3, plus 1. Now let's see if we can find some patterns, right? Something that works for every single term that we computed. Well, the first thing you know is that we have for each one, we have some 3's multiplied by 5. You can't see it in A0 because there's 0 3's. Maybe you can think of it that way. But for A1, you have 1 3 multiplied by 5. For A2, you have 2 3's multiplied by 5. For A3, you have 3 3's multiplied by 5. And A4, you have 4 3's multiplied by 5. So we expect AN to have n 3's multiplied by 5. So we get 3 to the n. And then the rest of them are powers of 3. Now, in the first two terms, that's kind of hard to see. But it turns out even the 1 is a power of 3 if you think of it as 3 to the 0. But you can see it more in A2. You have 3 plus 1. The next one, you get 3 squared plus 3 plus 1. And the next one, we have 3 cubed plus 3 squared plus 3 plus 1. And notice that we start with a power of 3 that's 1 less than the one we had in front of the 5. So we're going to start with 3 to the n minus 1, because the one in front of the 5 is 3 to the n, then plus 3 to the n minus 2, then plus 3 to the n minus 3, all the way down to 3 to the 1, and down to 1, which is 3 to the 0. All right, so I'm going to ignore the first term now, the one with the 5 in it, and just look at the other ones, because that should be a very familiar-looking familiar-looking expression. That is exactly our geometric sum, right? So our geometric sequence is 3 to the n, or 3 to the k, right? And then we're adding up the first n terms, the terms 0 to n minus 1 for that particular sequence. So it's a geometric sum, and the nice thing about a geometric sum is we have a formula for it. Now, you may not remember the formula for it. I'm going to let you look that up if you need to, or figure it out using the techniques that we use for geometric sums. But what you end up with is 3 to the n minus 1 over 2, which is a nice closed form for that geometric sum. And now that we have that, we can put that together with the entire expression for an. Remember, our an was 3n times 5 plus that geometric sum. Okay? So we're going to leave that 3 to the n times 5 alone. We're going to replace that geometric sum with the formula we just found, and we get 3 to the n times 5 plus 3 to the n minus 1 over 2, which is a nice closed formula for our sequence. So this technique that we use by looking at different terms and finding patterns is called iteration. All right, so now that you've seen these techniques in action, I think you're ready to work on the activities. The PDF file is called Telescoping and Iteration.